Hi, folks. Anybody here? Oh, it is a tough morning. It's rainy. Got a test last night. Might end up with only like 2 people. Anybody here? Say hi. Hello. Hello. Alright, I'm just getting myself organized here. How did the test go? Oh, and they're doing the lawn as well, which is great and convenient. Good morning. Nobody has any thoughts about how the test went. It's fair. Overthought them. That's a common thing. Yeah. Ooh, that's good. Easier than expected. I can work with that. Hopefully you all get good grades. Okay. Ooh. It's harder than expected. Uh-oh. Hi, Gabe. I'm just pulling out my notes here. It's one of those days, you know. Possible to give you a copy of the key so you can evaluate yourselves. Yeah, sure. I can do that, I think. Oh, oh, goodness me. There will be a review guide for the final. It's like the homework, but it doesn't help your grade the same way the homework does. Yeah. Okay. Whew. All right. Let's pull up this. All right. second to last class. Woo. Okay. So last stuff we're doing is chapter 12, which is all about rotational motion. Let me just make sure I find the right stuff. Rotational motion. Okay. My A looks weird. Rotational motion. So, we are returning to the glorious land of Omega and Alpha, period, and theta, all those good things. I'm sure you're all very excited. In case we do not finish this chapter in lecture, this is chapter 12. We are covering, let's see, 12.1 through 12.6, 12.7, 12.8. And not 12.9. Yes, 12.10. Not 12.11 or 12.12. Okay. So this is all the stuff that's covered, whether or not I get through all of it, but hopefully I will. Okay, so tell me what omega stands for. Wumbo. Yeah? Okay. What is it in words? If a question says, find the blank, angular velocity, good. Angular velocity. What units is omega usually in? Yeah, angular velocity, you got it. So usually it's radians per second. You might also see it, yeah, good, in RPM. That is also pretty common. Okay. So I'm going to add a little bit of detail, which is we have not yet talked about the sign of omega. So just like we have, there's the plus x direction and the minus x direction. We have a plus y direction and a minus y direction. So if our velocity is positive, that means it's going to the right. If our velocity is negative, it means it's going to the left, right? All this kind of stuff. We have the same thing for Wumbo. Wumbo is positive or negative. It tells you which way something is turning. Right? What are the options for which way something is turning? Clockwise and counterclockwise. Yep. Okay, which is which? Very confident from Michael, counterclockwise is positive, and you are correct. Clockwise is negative, counterclockwise is positive. How can we remember this? So there's a couple different ways. One is to think about the unit circle. right? So on the unit circle, you start at theta equals 0, and then as theta increases, right, you go to pi over 2, you go to pi, you go to 3 pi over 2. Yeah, so for the unit circle, theta increases counterclockwise. So that's one way to remember it. Why does theta increase going counterclockwise? I have no idea. I guess it's has to do with the fact that that's our x and y. So because we decided that positive x and positive y are to the right, just how it seems to work. Okay, there's another way to remember. Is our first right-hand rule. Right-hand rules are super useful. You're going to see a lot of these in physics too. So this is like a preview. Okay. Right-hand rules are ways that we define whether something is positive or negative when there's usually like two options, and it's a way to make sure everybody is doing the same option. Okay, so this right-hand rule is if you take your fingers and you follow the path of the circle, your thumb will tell you whether it is positive, thumbs up, or negative, thumbs down, right? So if you have something that is rotating counterclockwise, you make a counterclockwise circle with your fingers, you're going to get your thumb pointing upward. Positive, yay, right? If it is rotating clockwise, you make a clockwise circle with your fingers. In order to do that, you have to flip your hand over so that your thumb is down. Clockwise, boo, negative. All right. That makes sense. This is the start of some other stuff. So you have your fingers will wrap in the direction of rotation. And then you get your thumb up is positive, down is negative. All right. Give me counterclockwise rotation in the chat if this is making sense. Or not. Fine, it's a tough day. Yay! Oh. Okay. Okay. So, all right, some stuff up there. Okay, what about alpha? Tell me what alpha stands for. In words, alpha is John over on Twitch says angular acceleration, and you are correct. This is not centripetal acceleration, this is angular acceleration. So this is if it is spinning faster or slower. Yeah. So it is just like our A is delta V over delta T. Our alpha is delta omega over delta T. Okay, so what does it mean if alpha is positive? Okay, Michael says omega increases its speed over time. Ooh. John over in the Twitch stream has a better idea. So remember, what about regular acceleration? If A is positive, does that mean it's speeding up? It could be speeding up in the positive x direction, or it could be slowing down in the negative x direction. Do we remember this? Right? It's all about whether V and A are the same or opposite signs. Is what matters, not necessarily what the sign of A is. So alpha is positive, could mean speeding up in the positive omega direction, which is counterclockwise, or could be slowing down in the negative omega direction, which is clockwise. Okay. You can think of it as being a counterclockwise push, right? If alpha is positive. So you have a thing that's rotating. You're pushing it in the counterclockwise direction. If it's already going counterclockwise, you're going to be speeding it up. If it's going clockwise, you're going to be slowing it down. Does that make sense? So a little bit of practice here. A fan is rotating clockwise and slowing down. Tell me whether omega and alpha are positive or negative. Okay. I have a thought from Twitch, so let me see if I can get some thought from Teams. All right. What do y'all think? Are John and Michael right? All right. Nobody's totally sure, but good news, you're both right. So omega is negative, but alpha is positive. Okay. Making sense? Okay. So we are going to come back to this idea of a push. Okay. This is a specific kind of push. It's a push that makes something rotate. Not all pushes will make something rotate, right? You can push something and it just moves, right? Versus a push that makes something rotate. So we're going to talk about what this is a little later, but that is specifically a torque. It's a push that makes something rotate. And the specific definition really is a force that is applied off axis. Okay. What does that mean, off axis? What's an axis? X or y equals 0. So that would be true for, we're thinking about like the coordinate x-axis and y-axis, right? So that's true. We are interested in specifically axis of rotation. What's an axis of rotation? It's the kind of thing that's easy to understand, but not necessarily easy to put into words. No thoughts? Okay. If you think of something, go ahead and drop it in the chat. This is sort of the line that an object rotates around. So it's like where your omega is, or your v is equal to 0, kind of. So it's usually, it's often very easy to understand. So like a record, the axis of rotation is going to be a line through the center, right? So we are specifically talking about a fixed or a rigid body. What does a rigid body mean? It's easiest to understand this in contrast to a non-rigid body. So, are you familiar with ragdoll physics? It's like a video game term. Yeah. Yep. I think it's funny, so I'm going to play a little thing. So this is a situation where your body is an extended object, and the different parts of the body will move sort of separately. We are not going to be considering this. It is pure hilarity. I enjoy very much. Wow, that was more violent than I expected. There we go. That's better. Right. All the pieces are flinging around, right? I do love skateboarding games. We're not going to be doing ragdoll physics. This is too complicated for us. Gmod. I don't think I know Gmod. What's that? Gary's mod. I've heard of this, where isn't like everything is Gary for some reason. I forget what game it's for. So we're going to be talking about a rigid body where everything is fixed and together and it's not a ragdoll. Like we are going to treat a person as if they are frozen in place, right? So things that don't bend. Yeah, I remember it was a mod for something, but I can't remember the original game. I remember watching it. I watch people play video games way more than I actually play video games. Half-Life 2, that's it. I felt like it was either Half-Life or Halo, and I knew I was going to say something wrong. Okay, so specifically rigid body. So rigid bodies, all right, let's return to our actual physics. Will rotate about one axis, as opposed to a ragdoll where there's lots of different this arm is rotating about your elbow and this arm is rotating about the shoulder, right? It's the whole thing's rotating about one axis, and you have two options. You can have restrained or unrestrained motion. So restrained motion is sort of if you have an axis that is absolutely fixed in place, right? My laptop can only rotate about that, like the opening hinge, right? There's no other alternative for rotating the top of my laptop lid, right? The axis has to be that hinge. So this is often things that are attached to other things. This can also be stuff like a person falling down. They're rotating about the axis that is their foot. The other option is that there's no fixed axis. This is more like if you throw something up in the air, right? If I throw my pen up in the air, right, it's going to rotate as it spins. There is no fixed axis. It's not locked in place, right? This would be a fixed axis where it is rotating about the location where I am holding it, right? Versus if you are just sort of spinning it, right? Whee! It's going to rotate freely. Doesn't make any sense. If it is free to rotate, an unrestrained object will rotate about its center of mass. This is the point that stands still while everything moves around it. All right, let me pull up. Let me see if I can find. A good example. There we go. We're gonna get an ad for something here. Okay. So this is an example of tossing streaming a video over another streaming service doesn't work very well. So I'm going to see if I can post the link to this video so that you can watch it if on your own connection. Yeah, that's not working very well. Put it in Teams. Paste. Okay. And I'm going to stick this in Twitch as well. Paste. Okay. So if you watch this video, you will see that the hammer rotates. It goes up in the air, but as it goes up in the air, there's sort of one point that goes up in the air straight and comes back down straight, and the rest of the hammer is rotating. Can I draw? About that point. Right. If you throw a hammer horizontally, the center of mass will make a parabola, but the hammer, I guess it's shaped like a T, will rotate about that. Center. Does that make sense? We have a parabolic path of the center of mass, and we have the, oh, hello. The object rotates around it. All right, I got one thumbs up from Shannon. Anybody else? Yes, no, makes sense, not make sense. Awesome. Great. Okay. So how do we find the center mass of an object? There's a couple of options. If I gave you a hammer and said, put a dot on this hammer where the center of mass is, what would you do? Someone suggests throw it in C. Yep, that works. Look for the point that is traveling, that it's rotating around, right? That's one way to do it. There's another way to do it physically. It's going to be on or barely, near or barely on the head of the hammer. That's true. Is there a way to figure out exactly where it should be? Find the point you can balance it. Also true.
right? The point where you can balance an object will be the center of mass. We're going to talk about why this is a little bit later. It has to do with that idea of torque and forces being applied off axis. But yeah. And the third way is mass. So these two are super useful, but I'm unlikely to ask you to do them on a test. So let's talk about the math way. Math way. It's essentially the average of the location of all the material that's in your object. So if you have an object, let's see, what's a good thing to do? Yeah, the hammer works, right? So for a symmetric object, it's in the center. Hopefully that much makes sense, right? Symmetric object, it has to be in the center. So if we have a long piece of wood, it's going to be in the center of that long piece of wood. If we have a rectangle, it's going to be in the center of our rectangular prism, right? It's going to be in the center of that rectangular prism. If you have two objects, you average their center of mass. So if we have a, let's say, 20 centimeter long piece of wood, the center of mass would be 10 centimeters long. And let's say this has a mass of 500 grams. And then we have a rectangular prism that is, let's say, 2 centimeters by 2 centimeters by 6 centimeters. And it has a mass of 2.5 kilograms, right? And we stick these two things together. This is like our hammer, right? So here's our first center of mass. This is a bit Mjolnir-ish here. I like it. Okay. Where's the center of mass? Well, in our y direction and in our z direction, it's going to be halfway, right? So that's easy enough. It's symmetric. We are interested in our x direction. How do we find it? So what I can do, I get to decide where 0 is. X equals 0. Usually you put it at one end. If you put it at the center of mass of one of the objects, it doesn't work. So you can put it anywhere. So I'm going to put x equals 0 right here. Okay. So I have at x equals 10 centimeters. That is the location of the center of mass for my my handle. And then at, what is this going to be? 21. Looks right. 21 centimeters is the center of mass for my head of my hammer. So I am going to take the weighted average, which I think is really funny. It's not actually a pun, but it kind of is because it is a weighted average. So I take the mass of the handle times the x location of the handle plus the mass of the head times the x location of the head divided by my total mass, and that will give me the x location for the center of mass relative to the same x equals 0 position. All right, so it is 0.5 kilograms times 0. I don't actually have to convert this. I can leave this in centimeters if I want, but for consistent, just to make life easier, I'm not gonna. This is, what did I say, 2.5 kilograms. And this is 0.21 centimeters divided by our total mass is 3 kilograms. So our center of mass is located okay. I get 0.575 divided by 3 is 0.192 meters, which is 19.2 centimeters, which is like here, which makes sense. That's what we anticipated. It would be very close to the head of the hammer, if not inside the head of the hammer. Okay, so that is the center of mass for our overall object. Make sense? Yes? Yes, no, yes, no. Yes. Woo! Awesome. Okay. I am not going to make you do an example right now. I'm going to put it in a little Canvas quiz. So you can practice that. If I have lots of sort of objects, you do it for all of them. M1, X1 plus M2, X2 plus M3, X3 plus however many you have divided by your M total. You can write this as the sum of M I xi, and then you divide it by the total mass. So this, I believe, is the version that's on your formula sheet. And then if it is two-dimensional, like if you have a bunch of things attached, or if it's three-dimensional, what do you think you do? You do one for X, you do one for Y. Yep, X, Y, and Z coordinates. Okay. So what if it's not just a couple of individual objects? What if it is what we're going to call an extended object? So this might be a I don't know, blob. That looks like it just says BBB. Blob. We want to find the center of mass of this blob. What do we do? Any guesses? Split it into infinite symmetrical objects. We chop it up into little pieces. Each little piece is symmetric and its center of mass is at the center. So each little piece has a mass, delta M, and a center of mass at x comma y. And then what do we do with these infinitely small little pieces? I'm going to do my weighted average of all of these, which when you have lots and lots and lots of little pieces and you want to add them all up, that is called doing an integral. Good. Integrate. I will not expect you to do any super complicated integrating, but you may be expected to do some simple integrating. So this is like one-dimensional type stuff. So our x center mass would be the integral. Otherwise, adding them up would take all day. Yes, precisely. X dm. In order to do this, you have to change dm into dx, which we usually do by using the density of the material. So, for example, if you have a rod that is m kilograms and it is L meters long, you would have a density of m kilograms per meter, which is the same as the density of sort of the mass in this little chunk divided by the length of this little chunk. So what you can do is dm is equal to m over L dx. And when you integrate this, you actually end up getting x is 1/2 L, which makes sense because it's symmetric. I don't want to spend a huge amount of time on this. This is example 12.2 in the book, if you want to look at it. I don't think we're going to ask you to do this. Okay. All right. All good. Okay. Okay. So now that we know how to find the axis, awesome. Now we know how to find the axis. It will either be given or it will be the center of mass. Okay, let's go back and talk about this push. A push that is applied off axis. Torque. is a push that is applied off axis. So if we know where the axis is, then we know sort of where the force is applied. So there is also a secondary definition, which is that it causes things to rotate. Causes things to rotate. So we make this like connection between torque and force. So force is just generally a push or a pull. Doesn't have to be off axis, and it makes things accelerate. Right? A torque causes an angular acceleration. So there are two equations for torque. And this is where a lot of students get kind of mixed up. Is that these are not, it's not like one is right and one is wrong. It's not like you use one of them sometimes and the other times. It's like there are two different ways to look at it. So we have torque. I'm going to do the simple version, simplified version. We're going to talk about the longer version a little bit later. This is the non-vector version. Okay, we're going to do the vector version, I guess, maybe next time. Oh, lost a little bit of my Twitch connection there. Okay. Okay, so we have two equations. Which is the equation for torque? Yes, both. This is about the cause of torque. It is a force that is being applied off axis. This is about the result of torque, which is that we get an angular acceleration. Okay. Which one you use will depend on your problem. Often you will use both. Often you will use the cause to find torque and then use the torque to find the rotation. Okay, so we're going to talk about the cause first. So, cause equation. So the simplest way to think about this is if you imagine a door. You have a door. Door has a hinge. This is viewed from above. And let's say it's just like a swinging saloon door, right? We're not going to worry about a door jamb and which way it goes or anything like that. It's just like a door in a Wild West saloon. It just freely swings. So it has a hinge, which means this is a fixed axis. So we don't actually care where the center of mass is for this purpose. If we want to push the door open, we need to apply a force off axis, which means generate a torque. Oh, and I didn't really talk about it. This symbol is the Greek letter tau. Okay. Apply force off axis. So if you imagine in a cowboy movie, they walk in and they shove the saloon doors So there's going to be some push with some amount of force that is at some distance r away from the axis. Okay. Makes sense, hopefully. Okay. So if our cowboy pushes with, doesn't want to write, there we go, with 20 newtons of force at 45 centimeters from the hinge. Sorry, it's like freezing. Doesn't want to write. There we go. How much torque does he apply? This is a question for y'all. Nine torque, yes. You are correct, 9. And the units, Michael is correct, is Newton meters. Note that a Newton meter is a joule, but this is not a joule. It's just a Newton meter. It just lives as Newton meters. Okay. Making sense? All good. What about a larger cowboy comes up and pushes with 30 newtons of force, but his arms are further apart. So he is pressing the door only 30 centimeters. Let's say only 40 centimeters from the hinge. How much torque is this cowboy going to apply? Yeah, 12 Newton meters. So it depends on two things. It depends on the force and the distance. It is totally possible to apply a really big force, but if it's only 10 centimeters away from the hinge, this would only be 10 Newton meters of torque, which is less than the cowboy that was pushing with less force but further away. This idea of how far it is from the axis is sometimes called a moment arm. If you're a mechanical engineer, a torque is also called a moment. In physics, a moment just means a quantity multiplied by distance. So in physics, you see a lot of different moments. There's dipole moments and force moments and others that I can't think of off the top of my head. Moments of inertia multiplied by distance. But in statics, moment always means torque. And a moment arm is that distance away that you're applying it. Okay. So far, so good. What about that theta? We haven't really talked about this theta yet. So if we have someone who comes up and tries to open the door by like pushing on it from this end, is it going to rotate? Probably not, right? So yeah, you have to have an angle, right? So if I push right here, I'm going to generate more torque than if I push sort of I can apply the same force in 3 different ways, but I will get the maximum torque, 0 torque, and then something in between, based on the angle. Okay, what is this angle theta? So theta is the angle between that moment arm and the force vector. So our moment arm is from the axis out to the location where the, wait, let me make sure I'm doing this right. Yeah, out to where you are applying the force. R is from the axis to the force. And theta is our angle between R and F. So if, for these two, it would be 90 degrees. For this one, it would be, you're kind of looking at this angle, right? And then for this one, it would be 180 degrees, right? Does that make sense? So this is theta equals 90, this is theta equals 180, and this is some theta value in between. It says no. No, it's not making sense. It's a particular aspect that's not making sense. So for this one, the sine of 90, okay. Or, oh, it was the answer to the will it rotate? You said no. Gotcha. Sine of 90 is 1, so we get the maximum torque. Sine of 180 is 0, so we get no torque. Sine of whatever angle this is going to be some value, something in between. So let us consider. So have you ever seen people trying to bring down a tree? And this is sort of in a YouTube video that then ends up on some sort of collection, right? Definitely what trees look like. I should have done it in green, shouldn't I? Green tree. Okay. here we have a green tree, it's beautiful. They have chopped almost entirely through right here. So this is our axis. Right? That is the point about which the tree is going to rotate. In order to bring the tree down, they have tied a rope at a height of 5.5 meters above the chop. And they are standing over here. And because they are not very bright, they are pulling with 100, let's say 250 newtons at the angle shown. How much torque are they exerting? Okay, so let's say this angle is 55 degrees. This is obviously not a smart tactic because the tree is going to rotate and it's going to fall on them, which I think is pretty funny. Hence the YouTube video. Doing okay. All right, John has a number. I'm just checking. I have to do some sort of mental geometry here. I get a different number. So you have to be careful about your angle here. So our R is here. Our F is like this, right? F. Okay, this angle is 55. So this angle is 55. So theta is 90 plus 55, which is 145. So we have our torque is 250 times 5.5 meters times the sine of 145, which gives us I get 789 Newton meters. Questions, comments, concerns? I want to do one more thing before we end for the day. Same answer, hooray. John, does this make sense why it's 145 degrees and not 55? 55 is the angle from the perpendicular, and you want the angle from the parallel. Okay. So, tree starts to fall. You are still pulling with 250 newtons. But now we're going to draw a little bit different. You are still pulling 5.5 meters. You're right here. I should work out exactly where you were standing. You're like right here. So now this is more like 85 degrees. Okay. So the torque you apply is now tau times 250 times 5.5 times the sine of, okay, if that's 85, then that's 5. So make sure I'm doing this right. So this angle is 5. Let's say the tree has now fallen to a 45-degree angle. That's what I was missing. Okay. So this would be 45 degrees right there. This would be 5 degrees. This would be 85 degrees. So put this right here. This would be 5. So it would be 45 plus 85. Correct me if you think I'm wrong here. Yeah, because it was 90 plus 55 earlier, so 45 plus 85 makes sense. 130 degrees. So we have times 50 times 5.5. A little bit more torque, but not a tremendous amount more. But is there any other torque? If you stopped pulling entirely, the tree would still be experiencing a rotational force, right? Due to what? We're almost done. Gravity, yes. Due to the weight of the tree. Yes, there would be some initial angular velocity as well. That's true. But the weight of the tree. So now we have torque due to gravity. Torque due to gravity is really easy. The force is mg. It always acts downward, and it acts at the center of mass. So if our tree had a center of mass. Let's say it's right here. Is the top of the tree heavier than the bottom of the tree? I feel like it should be. Yeah. So let's say our center of mass is at 6.5 meters. And let's say our mass of the tree, chopped part, is 1,200 kilograms. So we would have a torque due to gravity that is equal to mass times gravity times the sine of our angle. So if this is 45 degrees, then this is 45 degrees. This is 90. So it would be 90 plus 45, so 135. $8,315 Newton meters. So the tree is definitely going to win here, right? This is a lot of torque. This is why this was a bad plan. Is even after you stop pulling, you have this much torque making the tree go onto your face, right? If we want to find the net torque, aka the total torque, what would we do? Almost done, like 2 minutes. Tell me what we would do to find the total torque on this tree at this moment. Nate, I just noticed your gravity, which is cute. Sum of the torque. Add up the torques. So it would be 1053, right? Plus 8315. But watch signs. Torque will be positive if it causes counterclockwise rotation. Torque will be negative if it causes clockwise rotation. In this case, which way does the tree want to rotate? Right, the torques are both making the tree rotate clockwise. So these are actually both negative torques. So we could say this is 9,368 Newton meters clockwise, or just negative 9,368 Newton meters. Just like you might say 10 newtons to the left or negative 10 newtons. It's the same kind of idea. All right, I'm going to stop there. Thank you so much. We've gotten through quite a bit. So I think we're in good shape to finish on Tuesday. And I will post a little bit of practice for you on Canvas if I remember. And yeah, hopefully I will. Any questions for me before I let you go? Thank you so much for turning up. Day after a test, I know it's not easy. Sneeze. Nope. All right. Thanks all. See you. Yes, let me put that on my to-do list before I forget. Okay. Upload key. Canvas quiz. Thank you all so much. Have a great weekend. Ooh.